Hello and welcome to Health Informatics 6220, Advanced Biostatistics and Health Analytics. Today's session 1.1, we'll be exploring the question of information and its role in the health analytics and data analysis. In terms of introductions, my name is Andrew Knighton. I'll be your instructor for this course. In terms of some quick background on my own experience, I spent 20 years in finance, most recently as a vice president of finance at United Health Group in Minneapolis. As part of a mid-career change of pace, I returned to school full-time over 3 years ago, and I'm currently completing a PhD in health informatics at the University of Minnesota. I'm a published health services researcher. Most of the work I've done for both the MS and PhD were conducted at children's hospitals and clinics of Minnesota. My research emphasis focused on looking at readmission risk in a pediatric asthma population, including developing methods for detecting asthma encounters using administrative data. My PhD work is currently looking at the impact of electronic health record on the incidence of test repetition in a pediatric Medicaid accountable care population. So in addition to research, I recently developed and taught the Health Data Analytics and Data Science course taught at the University of Minnesota. Currently, I am a senior clinical research analyst at Intermountain Healthcare in Salt Lake City, Utah, working within their Institute for Healthcare Delivery Research. And by the way, I'm also a certified public accountant, which may make you yawn. So let's start by asking a simple yet fundamentally important question in the field of health informatics and analytics, and that is, what is information? If you were holding information in your hand, what would it look like? So take a minute, pause the recording, and write down in 20 words or less your succinct definition of information. Now that you've put some things down on paper, perhaps a few definitions from the web might help. Information includes the communication or reception of knowledge or intelligence. So apparently, not all things that get communicated are necessarily knowledge or intelligence. For example, I'm thinking about my 12-year-old daughter's recent text messages with a friend. At this point, perhaps we can rule out most magazines you find in the grocery store aisle as well. The important takeaway here is that information involves the communication of knowledge or intelligence, things that are useful or of value. Another definition of information defines it as knowledge acquired through investigation, study, or instruction. Information in this context then involves some type of knowledge of facts. But this is my personal favorite definition of information. Information, this is taken from the field of information in economics. Basically says that information is a reduction in uncertainty. While perhaps somewhat abstract, which makes me wonder if the definition itself is really information, we can think of information as something that alters our thinking, that influences in some way our decision-making, either by adjusting our perspective on a decision or by reinforcing our understanding. All within an eye towards reducing the uncertainty that surrounds decisions that we have to make today in really any context. So when we think about information, there are several dimensions to the theories regarding information that have been developed. Claude Shannon in 1948 published his seminal work called A Mathematical Theory of Communication. His theory of communication, I think, is helpful in taking apart and understanding the elements of information. He defines the bit as really the basis of all communication. It's namely a choice between two equally probable alternatives. One way we can think about the term bit, and most of you have probably run across that in technology, is we refer to the bit as the 0 or the 1. That's the real basis of the collection and accumulation of data, within technology. So most of us are familiar with the bit in the context of computing, and this is really the same thing. Communication theory then tells us how many bits of information can be sent per second over perfect and imperfect communication channels in terms of rather abstract descriptions. Communication theory also describes for us how to measure the rate at which a source generates information. So there are 3 dimensions of information theory that Shannon identifies. I've highlighted much of the first dimension, which involves what I describe as this technical or engineering aspect of information, which is our ability to deliver it. Semantic aspect involves the meaning of information. What is the message telling me? What am I to understand from the communication? My son walks into the house one day and says that I ask him if all his homework is done, and he says yes. Knowing my son at times and his interest in other things that extend beyond his studies, I might have to think about the meaning of the message that he's delivered, and may have to take then really, which brings us to the third step of communication, which is the effectiveness aspect. How effective is the communication in conveying information, and how effectively does that information lead to some form of action? I think these 3 dimensions of information theory are essential to understand as analysts and informaticists. Let's talk as well then about some of the important properties or characteristics of clinical information specifically, because each property has important implications for a health profession, for the field of health informatics, and for your work as analysts. First is the property of growth. That is really the idea that health information is growing rapidly, and you've probably covered this in your health informatics courses. We are looking at an explosion in health data that's coming through investments in electronic health record technology, as well as through information that's now being captured in structured, semi-structured, and unstructured forms on the web. And this growth in information at an exponential rate is an important aspect of our property of clinical information. Second property of clinical information is the idea of obsolescence, which basically means that clinical information has a shelf life. There is a timeliness aspect to information delivery. And that's because either our understanding changes as we build upon past knowledge to gain current understanding, or information is only useful within a real specific context. For example, a clinician often places more value on the blood pressure reading and temperature readings taken by the nurse at the beginning of her primary care checkup than she might be of reading or taking interest in readings that were conducted 2 or 3 years ago. Current information is often but not always more valuable than past history. So clinical information has a property of obsolescence. It also has a property of fragmentation. Clinical research generally comes in pieces. While we enjoy the benefit of textbooks and other efforts that gather information into one place, it develops in fairly fragmented pieces that build knowledge, a piece at a time over time. So, for example, at a very simple level, the diagnosis of a patient may involve a number of data points that come in separate readings or measures. The role of the clinician, or the clinical researcher then, is to aggregate or bring those pieces together. And finally, the fourth property of clinical information is this property of linkage, or this idea of linkage, which says that while information is fragmented, it can be linked together into interesting and meaningful ways which are related. And I think as informaticists, as analysts, we are just at the front end of really beginning to understand what that means. So where do the concepts like data science and data analytics fit into this? Well, interestingly, the total information capacity of the universe, in case you were wondering, has actually been estimated. The information value of every cell and molecule of information, every atom, viewed in the context of ones and zeros, has been estimated at about 10 to 120 bits. Simply put, it's a pretty big number. The information of Homo sapiens is estimated at about 5 times 10 to the 18th bits. Not nearly as big a number, but yet a sizable number and growing. So how do we work with data of the volumes that are now being generated? How do we use data available to develop information and knowledge that improves mankind, both generally and in the field of healthcare? Well, the argument is that we need a distinct discipline known as data science for working with these large healthcare data sets. So in this course, we'll be exploring some of these tools and their application. You've been asked to read an article for this first class called Data Science and Prediction by Vasant Dar. I think this is an excellent article that begins to frame the real issues that are at play today when it comes to the development of data science and predictive modeling. He highlights several important key points. First, as we've already talked about, data volumes are continuing to increase generally and in the field of healthcare. The nature of data is evolving. More and more we're moving away from structured data sources to semi-structured and unstructured electronic data, which has interesting implications for the methods that are used in analyzing data. In terms of scale, we're starting to see a significant increase in the scale and the need to scale solutions for decision making, which brings some interesting implications. And finally, he talks about this idea of discovery. And discovery is the idea that rather than beginning with a hypothesis and knowing our outcome, or not knowing our outcome, but beginning with a hypothesis and then developing to some type of a conclusion, that we begin to use data in a more exploratory fashion as the basis for developing hypothesis. So that's a potential change in the way that data is used in the scientific process, which is, I think, particularly interesting. And finally, in terms of skills, there is a wrapping around or a wrapping together of a whole host of skill sets that have to come together to make this work. And perhaps early on you were wondering what a CPA is doing teaching a class on health analytics. And I think my participation here would be evidence of the fact that as we look at problem solving and data science and prediction, particularly in healthcare, we really have to bring together the talents and skills of individuals from a number of disciplines, from computer science, econometrics, sociology, linguistics, and even accounting. So it's a new era of exploration. We stand at the base of this new era and an opportunity to explore data in some new and interesting ways. And so I'm hoping as analysts or potential future analysts and informaticists, you're excited about the opportunities that are available as you move forward. Upon completion of this course, you should be able to examine and understand clinician, patient, and payer decision making. We're going to take a whole unit and explore how do decisions get made? How do clinicians think and make decisions? We're going to talk about the role of data types and attributes and their application and analysis, and as well explore the use of specific measurement methods in healthcare. And I think this type of a foundation helps a good analyst understand the problem that they're trying to solve. From there, then, we'll explore more specifically the use of analytic methods to improve quality, efficiency, and cost of patient care. We'll demonstrate data science methods that can assist not only in preparing data for use, but in applying those methods in classification, forecasting, and prediction, all within the context of problem solving in healthcare. And this is important because a good analyst then not only understands the problem, but then knows how to apply the right problem-solving methods in decision-making. In terms of grading for this course, there won't be any examinations. It's 8 weeks long. We'll have 7 assignments. These assignments are really exercises to practice skill development and use of real-world case studies. We'll have weekly participation in online discussion forums, both as a participant and then across the classroom. We'll make assignments up front to have each of you participate as the discussion leader, and you'll receive points based upon whether you're acting as the leader or as a participant. At any point in time for this course, I invite you to work together on your work, though it's important that each of you ultimately submit your own work. Now, for this particular week, this first week, you'll have an opportunity. I invite you to introduce yourself to the other members of the class, as well as to tackle one of the first questions. I'll go ahead and lead the discussion this first week and look for each of you to participate. So for purposes of this course, we'll be working with R. Hopefully you have had some exposure to R through biostatistics. If not, it is available for free online, and information has been provided on how to download it. Along with R, I'd encourage each of you to also upload RStudio. This application brings together the elements of the R software language into a useful integrated development environment, or IDE, for execution. I had worked with R independently for some time, and in finding RStudio here in the past couple years, found it to be a nice environment for working with what I think at times is a complex language. Before you get too concerned with your abilities in R, for purposes of this course, we will be providing you, in most instances, with the code that you will need to use to perform analytics in R. The emphasis of this course is not on learning applications. It's really on developing an analytic discipline and an analytic way of thinking within the context of healthcare. And so for the most part, we'll be providing code that you'll need to be able to apply using R and RStudio. What I like about RStudio is the ability to store and run code, to be able to manage and view your data sets, to monitor the output, as well as to access files, plots, packages, to run graphics, and to be able to save and export those graphics in a quick and accessible way. The other tool we'll be working with is Excel. Why is it important for an analyst to become familiar with Excel? Well, Excel is the all-purpose tool for analysis across all analytic disciplines. I can tell you that from years of experience with it. The benefits of using Excel include its flexibility, as well as its flexibility for performing any number of functions. Now, some of the challenges of Excel generally involve what is referred to as revision, which is if I put a model together in Excel and I want to go make changes to that model, sometimes those changes have to be done in more manual or disruptive ways than if I had programmed, say for instance, in a programming language, an ability to iterate or review or look at data. Now, I would say, though, that with time, Excel becomes more robust. I think there are a number of add-ons, add-on features, add-in features that are making Excel a much more powerful tool. I really like to think of Excel as kind of the place where an analyst sketches out solutions and frames the results. I've assigned this small text as background reading over the first few classes, and would strongly recommend, if you have an interest in analytics and in healthcare, that you take some time and become familiar with this book by John Wenberg. John Wenberg is one of the great healthcare analysts and researchers of our generation, who has used his data effectively to influence the debate on healthcare, which, if we think about what the role of an analyst is, it's to be able to put together research in ways that influence the conversation, whether it's within an organization or globally, nationally, whatever it may be. I continue in my own work, whether at Children's Hospital or now at Intermountain Healthcare, to encounter the influence of Wenberg's work almost daily in my work. So we'll discuss this some more in future classes, including having a discussion on this work here. Our first discussion will focus on your first reading. In addition to the book by Wenberg, which I would say again is a fairly short, quick text, this text for the course, Practical Data Science with R, is something I've run across recently. And I think it's a useful text and the kind of text that could become a nice reference guide for you. The book is brand new, just published here in the last 6 months. I think it's a good practical introduction to working with statistics in the field of data science. Good examples using R, including R code, so that you can begin to explore the use of R for yourself, familiarize yourself with tools. Now, both the Wenberg book and the Practical Data Science with R texts are available online. Both of them are fairly inexpensive. You might even be able to find copies that, particularly the Wenberg book, might even be available in the library. So let's take a minute, wrap up this introduction by going back to our definition of information. We've talked about data, we talked about information, but we've also talked about data and knowledge, and we've kind of lumped those all together, perhaps even discussing them in an almost synonymous way. And it's natural to do that. But for purposes of health informatics, I'd like to break these down further. Data, for our purposes, is really the lowest level of understanding. It's the bits of something, but without any context. So, for example, if I take the number 4.21, it's an example of data. It's just a number. We can add liters to it, but it still gives us very little context. I have 4.21 liters, so I have some sense of capacity, but I really don't know what it is about. I don't have any context for its application. So as a general idea, data really has no relationship to anything. If I contrast that with information, information is a higher level of data. It's data put into context, which means then it has meaning, it has some type of semantic to it, and it has potential. So let's take that example of 4.21 liters. If we think about it now, Mr. X had a force vital capacity of 4.21 liters on January 21st, 2002. Now we have data that's defined in a relationship to other things. It begins to have more value to us. Then we think about knowledge, which is really the higher level or the aggregation of information. That's where we think about information put into practice or into use. Information is internalized, it's generalized, it impacts decisions and actions in deriving value. In this example then, we may look at 4.21 liters, understand it relates to falling FVC levels, and then we may apply knowledge that says, when that's happening, it may suggest a lung function problem. So that information is knowledge which is informing our approach to medicine. Data, information, knowledge, and wisdom are hierarchical then, with one building upon the other. As the interactions and interrelationships increase, as the complexity of the information and data we're looking to solve increase. So then what is health data science and data analytics? To kind of wrap things up. Well, it's the gathering, the preparation, the presentation of data to support inferential learning and prediction, really in a nutshell. So it's important to keep that in mind as our goal. And to what end? Well, it's to build new knowledge, to promote learning in clinicians and patients, and to really reduce decision uncertainty and to bring more confidence to the practice of medicine. So if we're not achieving one of these three aims, we need to really rethink any analysis we're conducting. Our goal then, by doing that, is to foster the development of a more efficient, a more effective learning health system, something we will explore at the end of the course. Thanks.